Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will start the section carding, and as we know that carding is the most important process in the staple spinning system, and in that line the carding process, it's basically fibers are from the tuft form, okay, random tuft form. Only in this portion we get the fiber in the continuous strand, okay, which is the product of the carding is a sliver. So, from the tuft to sliver formation which we get in the carding, and also here the fibers get their individualized identity. Now, in the tuft form which we get in the bloom, we get the fibers in the tuft form, where if we pull one fiber, so the cluster of fibers will be pulled. But in the carding what we do, we get the fibers in the fibers will have their individual identity. In that after carding, if we try to pull one fiber, the individual fiber will slide up. So, that is possible. So, to actually if we want to form from the cluster, if you want to have the fiber with a individual identity, we need to have some pins. So, like it is resembling our hairs, okay, after taking bath. So, it hair becomes say entangled. So, entangled hair, if we try to actually open up, and we need pins like our hair comb, and in that case the fibers get the separate identity like our hairs. So, this is done by the action of series of pinned surface. So, here we do not use the comb, but we use the surface where with a full of actually the pins. So, that is the basically the carding action. Now, here in this section we will discuss the carding action. Basically separation process of fiber tuft between two interactive wire cover surface. So, that is important. So, here we need two interactive wire cover. In our basically in our hair, what happened, this is our skull and this is our hair, okay. There some one surface is there which one end of our hair is actually attached with the our head, okay, our body part. Now, other part to we have one part is attached, for other part we need one single series of comb which will actually give the fiber, which will be passed through the hair, and we get the individual identities. We can actually open up the hair, but in case of fibers, fiber tuft, single surface is not enough. If there is a single surface, there has to be something which will hold the other surface there, otherwise this will simply move with this surface. So, there should be another surface which will have some, it will actually prevent this, there will be should be some resistance, then only the tufts will be opened. So, separation process of fibers. So, fiber separation process is actually achieved by the pair of wire covered surface. So, that is a basic idea of carding. So, you will see here, this is actually the typical diagram representation of wire points, and you will see the wire points are inclined just opposite direction to one each other. Okay. So, this configuration is known as point to point configuration. In the point to point configuration, these are they are actually aligned in opposite direction, and degree angle of inclination is alpha. Now, the necessary condition is that here there should be two wire surface facing each other. As I have mentioned, there must be two wire surface, single wire surface will not work, even more than two is not possible, okay, because they are facing each other. That is the first necessity. Second necessity is the distance between these two wire points. It cannot be 0 or very low, because otherwise they will touch. It should not be so such that they are touching each other, and then otherwise it will damage the wire point if it is too close, because these two surfaces they either move in opposite direction or in the same direction, but there will be some relative motion, okay, that due to that there may be some damage, or the this distance should not be too high. If the distance is too high, then it will not give the resistance to the fiber tuft. Okay. So, this distance, suppose this distance is too high. So, there if the fiber tuft is here, so that the other surface will not give some resistance, interaction will not be there. So, it will simply take out the fiber. So, that is not required. So, for that we need a particular minimum distance, so which is around 0.3 millimeter. So, that distance should be there, it should not touch or it should not be too high. If it is more than say 0.5 or that millimeter, so then the proper interaction, that opening action will be, separation action will not be achieved. And then the wire points should be opposite to each other. So, this wire point direction should be opposite to each other direction to have the opening action, which is carding action, and if it is in the same direction, then the opening will not be there, fiber will get transferred to the surface which moves at the higher speed. So, that is also not possible. So, we need to have the direction of actual wire points opposite to each other. The surface should be actually it should move in the same direction or in the opposite direction, that I have mentioned. This thing we will discuss separately in detail, what are their implications if it moves in opposite direction or in the same direction. But the condition is that even if it is moving, they are moving in the same direction, but there should be some relative motion. Otherwise, if they move in the same direction in the same speed, then the opening action will not be there, that there will not be segregation, separation will not be there, simply they will carry the fiber along with them. The surface charged with the material should move at faster rate if they move in the same direction. That means, if they are moving in the same direction, the surface which is actually charged with the fiber, that is full of fiber, it should move at the faster speed. Now, let me discuss this one. Suppose this is moving in the A direction, this direction, same direction, they are moving in the same direction. Now, what happened here, if you see, if we are having some fiber, these are the fiber, this surface 1 and this is 2 surface, this is actually carrying the fiber along with it. If it is moving at the first V1 and V2, if in case of V1 is less than V2, if V2 moves at the faster speed, then what will happen? This will simply move at the faster speed and this surface 1 is taking the fiber, it is waiting for the fibers to get opened, get resistance from the surface 2, but as surface 2 is moving at the faster speed, it will not have any impact on the fiber opening, fiber segregation or fiber individualization, okay, because it will not have any resistance. But on the other hand, in normal case, so that is why it is not done. But the thing is that when V1 is more than V2, in that case what happened, the surface of the wear points in the surface 1, it is moving at faster speed and the surface 2 moves at slower speed, and the surface 2 actually gives some resistance and fibers, the fiber tuft is teared apart and gets individualized here. So, they are individualizing the tuft and forming a single fiber, and in actual practice, in carding, during carding action, the higher movement. So, V1 is more than V2, 1 and 2 surface, this is actually cylinder, surface 1, and surface 2 which moves at slower speed, which is this is flat in the carding zone. In carding zone, this is a cylinder moves at faster speed and flat moves at slower speed. Now, for effective carding, these are the different derivation now we will be doing. Now, this is the point to point configuration, and here this is one surface, suppose it is a cylinder surface, and here it is a, this may be cylinder or maybe any other side. So, this is one surface and this is surface 2. Now, what we are getting here, you can see that this is called point to point configuration, because they are in the opposite direction, their angle of orientation of the wear points are opposite direction. Now, we are now trying to analyze the force on a fiber in between these two wear points. So, the red color it shows one, here it shows one fiber is attached between these two surfaces. Okay. Suppose this is flat and this is cylinder. Okay. Now, here the force on the fiber is termed as S, R 4. With R force, the fibers are being forced, and this R, this load on the fiber is, we can actually have two components on this. One component is P 2 another component is P1, and the angle here, angle of inclination is alpha. Now, you can see this is also alpha because it is a these are the parallel line, and here this has got two components. This two components is P1, R has got two components P1 and P2, and P2 as per the, if we actually have these two components, P1 P2 component is R cos alpha, where this is R alpha, and P1 will have R sin theta, because this angle is 90 minus alpha. So, P1 will be R sin alpha. So, P1 is R sin alpha. For effective carding action, fiber should stay with wear point. So, because it should not move out of the wear point, otherwise if it goes slips out of the wear point easily, then carding action will not be there. So, it should be actually, it should stay with the wear point, it should not come out of the wear point. So, P2 is more than, so P1 is actually at a right angle of this, and P1, this P2, this component which is actually holding the fiber, P2 component is trying to hold the fiber with the wear point of cylinder, okay, cylinder wear point. So, P2 should be more than P1, and the mu is the coefficient of friction between fiber and the wear point. So, fiber and wear point. So, this force is actually acting, P1 acts as the normal force. So, mu P1 is the frictional force. So, P2 should be more than the frictional force, then the fiber will be staying on the, will stay on the wear point for proper carding action. If P2 is less, that means the holding power of the this wear point is less. So, it will simply slip out of the wear point. So, that is the basic condition. Now, what is that? R cos alpha, the P2 means nothing but R cos alpha is more than mu R sin alpha. So, and cos alpha by sin alpha, R will get cancelled out, cos alpha by, that is cot alpha is more than mu. So, if we see this, so cot alpha will be more than mu, that is the condition. So, that is the condition. So, mu we can either we can change the mu, we can reduce the mu fiber, or we can change the cot alpha. So, lower cot alpha, so lower alpha. So, this lower angle, if it is angle, so cot alpha will be high. So, that in that case proper carding action will be there. So, that condition we have to maintain depending on the type of fiber. If the type of fiber changes, the mu will change. So, accordingly we can change the alpha. So, inclination of wear point is very important in carding. So, for in case of cotton, so you can see alpha will, in case of cotton it is lower than in case of wool. Cotton is less than 74 degree, because lower cot value means higher, that is value will be higher, that means lower angle, the cot alpha will be higher. So, for cotton we need higher value, because the fiber length is less. So, in that case, So, that holding power has to be increased. So, we need lower inclination for wool as the fiber lengths are high. So, in that case we can have little bit higher this angle alpha, because in case of wool if we have lower angle, the problem would be that it will be actually entangled with the wear point, because that cot alpha will be very high. Okay. So, that we have to have some compromise. Now, the how the fiber gets transferred from one surface to another. So, fiber has to be get transferred from one surface to another. So, that is actually called stripping action. In the stripping action, the direction is entirely different. It is called point to back configuration. So, their direction of the fiber movement will be direction of the wear point are in the same direction. So, they this in this case they may move in the same direction or opposite direction, but so they will be moving in the same direction or opposite direction. Normally, in the case of cylinder and Licarin, they move in the same direction. So, here we have suppose one wear point and the surface, this surface is carrying the slower, this is slower and this is faster. So, if slower surface is carrying a fiber, the surface which moves at the faster surface, so it will get transferred. So, from the slower surface the fibers get transferred to the faster surface. So, in case of Licarin and cylinder A, so Licarin is the slower surface and cylinder is the faster surface. So, fibers get transferred from Licarin to cylinder, that is called, this process is called stripping action. So, necessary conditions for stripping. So, there has to be first two condition same, first two conditions are same as carding action, like there should be two surfaces, two covered surfaces of wear points with wear points, and distance between the two interacting surface should be around 0.3 millimeter. If it is more, then effective more distance, that the fibers will not effectively get transferred to the faster surface. And the third one, which is different, is that the surface may move either in the same direction or in opposite direction, that also is possible there, but the wear point directions are the same. If they move in the same direction, the speed of the surface on which the material is to be transferred should move at higher than other surface. So, it will move like here in the cylinder and Licarin, as I have mentioned, cylinder is moving at higher speed, that means cylinder will take the material from Licarin to its surface, and direction of the wear point should be same. So, that is the condition which is different from the carding condition. Now, let us see the force applied on it. So, here they are in the same direction, point to back configuration. Here force applied on the surface fiber is much less than the carding action. Now, this one is the faster surface, suppose cylinder, and this is a Licarin. Okay. Likarin, it moves at slower speed. This is fast speed. Okay. Now, this is point 2 back configuration. Here again we actually get the force. R is the force applied on the fiber. Now, alpha is the angle of inclination or the front inclination, beta is the in this with the surface with the direction of the base, with the base the outer surface of the wear point is the beta angle. Now, theta is this angle. So, theta can be correlated with alpha and beta. So, S1 the force, the R is the force on fiber. So, it has got two components S1 and S2. Now, the beta is that same angle as I have already mentioned. So, this is actually S1 we can get it. So, R sin beta. So, this is a 90 minus beta. So, this become S1 becomes R sin beta and S2 is R sin theta, so cos beta. So, this is R cos beta and R sin beta. So, here you can see for effective stripping action fiber should move away from the wear point. So, fiber should move away from this wear point, and for effective carding action we have mentioned fiber should stay on the wear point. Now, here if you want the fiber to move away from the wear point, that means this S2 should be more than mu S1, that is this S1 and mu is there. The S1 force is the normal force applied on the this wear point. Okay. Here we want the fiber to slide off from this surface, and that is why S2 should be more than mu S1, and here. So, R cos beta, so here replacing S1, R cos beta is more than mu R sin beta, and that means cos beta is more than mu. Earlier case also what we have seen, cos alpha is more than mu, here cos beta should be more than mu to have proper. So, this cos beta should be, so cot beta should be more than mu. What is cos beta? Beta is nothing but alpha minus theta, this is alpha minus theta. So, this will be, so cot alpha minus beta will be alpha minus theta should be more than mu. With this condition we can achieve the proper stripping action. So, now we will discuss this till now we have discussed the carding action and stripping action and their different forces acting on a fiber and the condition for stripping and condition for carding, that these are the basic condition. Now, we will go step by step. So, at feed section what is going on? It consists of the feed device and a likarin with associated parts, that is a feed section. Feeds the here fibers are little bit opened. Now, you can see here. So, this is the feed section. Here this is the yellow colored, it is a feed bat. So, fiber bat, it is coming from the chute feed or maybe in the from the earlier system it was a lap. Now, this is the feed roller and here is the feed plate, and the feed roller has got some tooth, or maybe it has got some gnarled portion, and it feeds the material. Here the gripping is there at this point, and the Licarin takes the fibers in it, which it rotates anti-clockwise and takes the fiber at downward portion. So, here the feeding takes place, and in the, this is the conventional type feeding, and in the modern feeding system, shape of the feed plate it is in like this, and where the fibers are getting opened in the Licarin. This is the Licarin surface. Now, function is that to feed the material uniformly to the Licarin. So, that is the it is a basic function of feed section, to reduce the top size without causing damage to the fiber. So, here that is an important factor, which we should not damage the fiber. So, we reduce the top size, which will be ready for further carding. So, in blow room our top size is reduced, but further reduction to a very small top size is done at the Licarin portion, and to eliminate trash and short fibers there. So, in this feed section, so we also eliminate trash particle, but trash particle should not go to the carding zone, otherwise it will damage the cylinder wear points. So, we try to remove as much trash particle possible in the Licarin under casing Licarin grid zone. Okay. Now, let us calculate the force applied on this, how is it actually affecting the feeding. Now, this is the feed plate, and here is the feed roller, and feed roller is pressed against the feed plate with certain pressure. So, P is the top pressure, and in between the feed plate and feed roller these are the fibers. Fibers are placed in between, it is feeding, and it is pressed against that. Okay. Now, here the feed roller is moving at the anti-clockwise direction, that means it is trying to feed the fiber in from left to right side. But there, in addition to this pressure, there is a frictional force acting on that. There are two type of frictional forces. One is the friction between the feed roller and the fiber, another is the friction between feed plate and fiber shaft. So, this interaction between these two feed frictions, so which will affect the proper feeding. Now, see where the F1, what is F1? F1 is the mu r p. So, it is P is the top pressure, roller pressure, so feed roller pressure, and it is actually pressing the fiber bed against the feed plate, and when it rotates in the anti-clockwise, so it will try to pull the fiber, it will push the fiber along with it due to the frictional force F1. So, F1 and mu r is the frictional coefficient between the feed roller and the fiber mass. So, that is why we are getting F1, and mu r is the coefficient of friction between the fiber mass and the feed roller. So, this acts at the upper surface of the fiber bed. Now, F2, which is actually resisting the fiber movement, resisting the feeding. What is that? F2 mu f into p, p will be remaining same, and mu f is the coefficient of friction between the fiber mass and the feed plate. So, these are the two forces acting on the fiber mass. So, to the condition to move the fiber from for feeding, for uniform feeding. So, F1 should be more than F2, otherwise the fibers will slip past the the feed roller, and fibers will not be feeding will be interrupted. So, for uniform feeding, the sliding should take place at the bottom of the fibers, the plate at the bottom surface, that is against the feed plate. So, that is why to reduce this mu f, we use the very smooth plate. So, F1 has F2 has to be reduced. To reduce it, we need a very smooth feed plate, that is lower the mu f. Okay. Hence, mu r should be more than mu f. So, because AP is constant, top roller pressure is constant. So, we should maintain the friction, coefficient friction in such a fashion that the friction between the feed plate and fiber is lower than the friction between the feed roller and fiber surface. So, feed roller surface is typically we use in a rough surface with higher frictional coefficient. So, well designed feed device is expected to perform the following tasks. So, we have to design the feed plate in such a fashion, it clamps the fiber bed over the full width. So, the fiber bed, the width is there, suppose it is a width is 1 meter width, it should clamp the fiber uniformly. If it cannot clamp uniformly, then the problem would be that the Licarin will actually pluck the fiber where the pressure is less. So, that it should be uniformly clamped, so that the angle or direction, there should not be any uneven surface in the either in feed plate or feed roller. Because see, if we see if there is a feed plate, okay, feed plate, if feed plates, and here is a feed roller surface. Now, if the feed plate there is some bend is there. So, at where the opening is more, in that case your fiber will not be gripped properly. So, the Licarin will not be able to open the fibers properly. So, the fibers in the clump form will be picked. It should be able to hold the material back against the action of the liquid. So, it should not, fibers should not actually come out from this surface. The pull should be enough, because it should actually feed the fiber at the speed of the feed roller. So, this friction should be high here, sufficiently high, so that fiber should not be actually taken away by the Licarins easily. And in that case, so top roller pressure should be high, and this friction between the the feed roller and the fiber should be high, so that it maintains the fiber, it should retain the fiber. Okay. It should hold back the fiber, otherwise Licarin will take away the fibers easily. It presents the bat to the Licarin in such a manner that its opening can be carried out gently. So, that is also important. So, in that case the latest design of opening roller feed roller and the feed plate is there, that I will discuss separately, so that it gets gentle action in the Licarin. If we in the old system, the action was little bit harsh. In the conventional feed system comprised of stationary feed table with feed plate and feed roller pressure against the plate. So, in the conventional system there was a harsh treatment, but in the latest system it is the feed plate is formed as a special extension of feed table and is adapted to the curvature of the cylinder, that is cylinder, it is basically Licarin cylinder, it is a, so that is a special curvature, so that it holds the fiber against the Licarin surface. Here cylinder does not mean the our in carding cylinder, it is a Licarin here, because as it is cylindrical space shape, that is why it is telling. Now, you can see here that here the curvature is there, the curvature it is basically it is holding the fiber, the length of the guidance surface also influence the waste elimination. So, it should be more, if the surface is too long, it presses the fiber into the clothing, this gives better take up of fibers. Okay. So, it is but at the same time better take up of impurities also. So, if it is too long, then what will happen, it will actually it will entrap the impurity and the reduction, it will cleaning effect will be reduced. So, it should be optimum. Okay. Length of the guidance surface, that is guide surface, is dependent on the staple length. So, how much the length will be there, this guide surface, that depends on the staple length. We will discuss this, or mean length of the fiber, and at least within the range. So, that guidance surface, how long will be the guidance surface, that depends on the staple length. Higher the staple length, we can have higher that guidance surface. Now, this is the geometry of feed plate. Now, we are geometrical representation of this feed plate is there. Now, here we will see this is the Licarin tooth, these are the Licarin tooth, and the feed plate is here, the fiber bat or lap is fed, this is the feed roller and gripped up to this point A, and now with this the lap is moving in this fashion, and the first tooth of the Licarin is touching at the point D, okay, which is in the upper surface. At the lower surface, this is touched at the point E. So, that is a system. So, total fiber length, sorry, the lap length A, B, C, D, where A is the gripping point, last gripping point with the feed roller, and D is the point where the upper surface fibers presented at the upper surface is under the action of the Licarin. Similarly, for bottom of the lap, A dash is the point where it is gripped and E is the point. So, A is the distance where the fiber is first interacting with the Licarin tooth. Okay. Now, the diagram is shown here, same diagram. Now, try to see the distance between the nip is top nip is the A, this is the nip A, and the entry point of the Tekarin teeth into, this is the entry point of the Tekarin teeth into the top layer. As I mentioned, it is A, B, C, D, this is the distance, entry point, which is equal to 1/4 of the staple length, that we try to keep. So, 1/4 of the staple length if it is L by 4. So, that is the relationship. So, as the L length is staple length is more. So, we try to keep the setting more. Okay. So, here now 1/4 of the staple length. So, rest 3/4 are there, which is under the grip of the feed roller, and as it moves, so it will keep on interacting with it. So, more and more opening action will be there. It consists of considering the efficient of fiber straightening. So, that is the coefficient of fiber straightening is 0.5. So, for 0.5 coefficient of fiber straightening, it should be 1/4 of this. So, if you want to increase this length, so coefficient of fiber straightening will be affected. Now, the distance between the bottom portion. So, nip A dash, as I have mentioned, nip A dash and the point of entry of liquor into at the bottom layer E. So, bottom layer E should be equal to modal length. So, top layer it is 1/4 of staple length and this should be equal to the modal length. That is the based on the experiments, based on the experience, it has been actually decided. So, with this assumption we will proceed. So, ABCD is the equal to L by 4. So, 1/4 of the staple length. Now, A dash E equal to this, we can divide. A is the width of this plate and B is the this distance, straight distance here. So, this is nothing but AE, nothing but A plus B, where A is this width and B here this distance A plus B, and LM it is a modal length. So, LM is the modal length, L is the staple length, LM is the modal length. Now, try to see here. Now, what is ABCD? ABCD is nothing but this A, approximately this A distance A, and then this carved line, carved A, that is the BC. BC is the this carved distance. So, carved distance, the where the angle is here, if it is a beta angle. So, this is 90 minus beta. So, and this carved length is r, that is 2 pi d, this distance into theta. So, 2 pi d by 316, 2 pi d means the depth thickness of the layer. So, 2 pi, so r theta, so this is the theta. So, 2 pi d by 360, that means it is a this arc distance, arc length is the 2 pi d by 360 multiplied by theta 90 minus beta, and then it is a CD. CD is nothing but then CD this distance, this is the distance CD. So, here if we see, which is nothing but L by 4. Okay. L by 4, where D is the lap thickness and beta we can see from there, we can from this equation we can actually rearrange the equation and we get beta equal to this one. We just move here all this and then we get the beta value. So, by rearranging, this is the beta value we are getting. So, combing length, the length of fiber to be combed by the liquoring. Okay. This is the combing length, and for top layer of the lap, it is the staple length minus ABCD. So, total step, that is I mentioned the staple length, it is L and minus L by 4, ABCD is basically typically around L by 4. So, 3 by 4 L, rest 3 by 4 is the combing length. That length we actually it is average, this approximate value. So, this is the length we get the get to actually comb. So, rest of the things will, if as soon as it comes at this stage. So, when during starting point the fiber is there. So, and then it will start combing. So, that length is the combing length, but here you can see L minus ABCD, this L minus ABCD, this length is the combing length. So, that is the length available for combing in by the liquoring. This is for top layer, and for bottom layer it will be L minus A plus B. Total length, this is the total length, staple length minus A plus B, that is the for bottom layer. That means, combing length for top layer and bottom layer are different, and this is the length where the fibers are gripped and it is allowed to be combed. But when as soon as this fiber is actually released from the gripping point, so this will not be combed, it will directly be pulled by the liquoring. So, that is why combing length is the length which is actually L minus the step the ABCD for top layer and L minus A plus B for the bottom layer. So, this L A plus B from the bottom layer, and degree of combing at liquoring is the number of wear points acting per fiber. So, that is also we can calculate degree of combing per single fiber, how many liquoring wears are actually acting. Now, this is the degree of combing, number of wear points passing through the material per minute and number of fiber fed per minute. So, the number of wear points per is actually acting per fiber. Number of wear points passing through the material per minute equal to, so it depends on the liquoring RPM. So, if the liquoring RPM is high, so number of wear points passing through per material will be high. Number of wear points in the wear point density in the liquoring, if the wear point density in the liquoring is high, then number of wear points passing through per material per minute will be high. So, that we can control. So, these things are the numerator is affected by these two parameters we can control, and number of fibers fed per minute, that means how many fibers we are feeding per minute is depends on the fiber denier or thickness of lap. So, lap or bat linear density, if the thickness or linear density is high, then number of fibers will be more, and length of fiber or linear density of fiber, that is also important. So, this degree of combing we can control by all these parameters, okay? And higher degree of combing means better opening action. now feed in the same direction as Likharin rotation, that is unidirectional feed. Now, this is one development where which actually acts the which is actually gives the smooth action at the Likharin. So, fiber breakage is less. So, here you can see that this is the feed feed roller, but feed plate is not placed at the bottom. Feed plate is pressed against the feed roller from the top. Now, here you can see when the material is fed and material moves in the same direction to that of Likharin direction, and the curve due to this feeding the material gets the smooth action. So, the breakage is reduced. In the conventional system, the material is pushed forward illogically against the direction of the Likharin. So, it is actually move against the direction, okay. But in the modern feeding system, material is fed towards the direction of the Likharin rotation. So, the bat undergoes a sharp bend in the conventional feeding. So, where feeding is done like this, this is the feed roller and feed plate is there, and feed roller feeds the material in this direction, and then Likharin comes to action, where the sharp bend is there, that we have shown earlier. So, this gives a harsh action on the fiber, but here in this can sweep through it, this diversion certainly does not contribute the gentle fiber treatment. Here the harsh treatment is there, but in the modern system the treatment on the fiber is a soft treatment. The arrangement of these two feed devices is opposite in the new system. This it is basically just opposite. Opposite means the feed roller rotates in the opposite direction, it is a clockwise direction, and also the feed plate is placed at the top. In conventional system it was at the bottom. So, these two changes makes the system very smooth. So, owing to the rotation of the feed roller in the same direction as that of Likharin, here the bat runs down without diversion and directly fed into the teeth of the roller. It is directly fed into the teeth, and here only thing beating action is not there, but only the Likharin where point tears the fiber, actually takes the fiber smoothly and it is fed to the cylinder, and here the fiber breakages are less, cleaning action will be perfect. Okay. And now in the Likharin zone you can just, we have discussed the feed zone. Now, in the Likharin zone, to tear apart the lap into minute tufts without damaging the fibers. So, we actually we are not here, we do not damage the fiber, that is the function, is that to separate the trash particles and short fibers. So, the function is that to transfer fibers to cylinder surface smoothly. And now, let us see how to extract the waste at Likharin zone. The waste is eliminated in the Likharin zone. The waste elimination is very intensive here and takes place under the Likharin by means of special device. These are the special devices, it is a grid bars are there. Okay. In classical assembly, they consisted of 1 or 2 mote knives and a grid. So, these mote knives are there and grid, one half of which was made a slotted sheet and another half is perforated sheet. So, these are slotted sheet and perforated sheets in the classical system, and in this arrangement elimination of foreign matters took place exclusively by scrapping of one mote knives on the mote. So, here the foreign particles are scrapped off. So, this is a problem. So, sometimes it actually damages the fibers. Okay. The grid sheet tends to serve as a device to guiding and holding back the fibers, that is they prevent the additional fiber loss and could arise from ejection. Okay. So, that fiber, the grid sheet is actually it follows the curvature of the Likarin and which actually prevent the fiber loss. Now, waste elimination is very intensive and takes place under the Likarin by means of special device here. In classic cleaning assembly consists of 1 or 2 mote knives, grid one half of which made slotted sheet, that I have already discussed. Okay. Now, in high performance card, okay, in a modern system it requires alternative assembly, okay, in order to be able to deal with the high material throughput. So, the main problem with the high performance card is where we are throughput speed, material feed speed, high production. So, material throughput speed is very high. So, that actually normal system, it does not actually, it is not able to handle that much of material, because it will if we use at the high speed, the cleaning efficiency will be poor. So, we have to actually redesign this, where we have seen discuss the feed roller moves at the feed the material in the same direction, and accordingly the Likarin of such cards are no longer operates with the grid bar. So, grid bars is being eliminated and now carding segments are there, where in the Likarin instead of the grid bars, okay, we use the carding segment. Here one carding segments are there. This is the carding segments are placed in the last but one generation card, the latest generation. For example, the tufts are first guided over the mote knives. This is the mote knife, it is guided over the mote knives, then over the carding plate 3. This is the carding plate. So, carding plate actually helps in little bit opening against over the mote knife, again over carding plate before they finally move into the cylinder. So, here one carding plates are also placed. Okay. Now, you can see here this type of carding plates are there. Are fitted with special clothing. So, that is shown, this is a type of special clothing in place of grid bar, here it is a carding plate is placed. So, mote knife, main problem with the mote knife is it causes the air vortex. So, this is the plate mote knife plate. Now, once the fiber Likarin moves at high speed, the air passes through this from the Likarin, and on the other side the air vortex is created. What happened? The air vortex tries to push the air back, and whatever the fibers and trash particles are being eliminated, they can, there is a possibility they can come back once again. Okay. So, vortex has a tendency to redeposit the ejected trash particles onto the Likarin surface. So, cleaning efficiency gets affected. So, in the that is the problem of the mote knife. So, degree of cleaning can be improved if we at all use preventing the generation of air vortex. We can try to prevent the generation of air vortex, weakening the strength of vortices, increasing the intensity of opening. If you can increase the intensity of opening. Now, the intensity of opening depends on. So, we can do all these things to have more cleaning efficiency. So, air vortex we can actually, it is very difficult to control, because if we use the mode 9 that will be definitely there, but if we increase the intensity of opening, then we can compensate little bit. So, intensity of opening, that depends on the feed material parameter, we can control the feed material parameter, then liquor in parameter, there are different parameters are there, then processing parameters. Now, we can see the feed material parameters are the that is the feed material, the bat linear density. So, if we increase the bat linear density, then intensity will be more. So, degree of openness of the tuft in the bat, degree of orientation of the fiber in the bat. So, that all this controls the intensity of opening, and liquor in parameter, wear point density and inclination of the wear point, that these affect the this intensity of opening. And processing parameters are settings, definitely if we are having closer setting, then intensity of opening will be high. Rotational speed of the liquor, higher rotational speed will have higher intensity, throughput rate, and more number of combing position by the increasing the number of rollers or by adding combing surface. Okay. Now, that is all with this section. So, we will start a new session in the next session, new topic. So, till then, thank you.